Tesla has been a roller coaster of a stock for the past few years. With over 2,000% growth, it has become a hot topic for all levels of professional investors. Some may attribute its growth to the manipulation by executive Elon Musk, others to simply sheer luck. However, we think that Tesla has grown so much is because of its amazing electric cars.
Tesla wasn't the first company to make electric cars, as the start of electrically powered vehicles came from the discovery of rechargeable batteries, specifically the rechargeable lead-acid battery in 1859 by French physician Gaston Planté. By 1881, William Morrison created a 6-passenger wagon that was powered solely by electricity from batteries. In the 1950s, cars stopped using solely electricity and shifted to gas power. By the late 1900s, companies were encouraged to create hybrid vehicles in a climate action initiative, and by the 21st century, fully electric vehicles were back and Tesla is leading the way.
So what makes a Tesla car battery work? Well, like every other battery, they undergo redox reactions to generate current. A redox reaction is when a reduction and oxidation reaction occurs at the same time. What this means is that an atom loses electrons, which is oxidation, while another atom gains electrons, known as reduction. Chemically, this can be broken up into two half reactions. For example, copper and zinc in a Daniell cell works with the oxidation of zinc. This process turns solid zinc into electrons and zinc ions. Simultaneously, a reduction reaction occurs, turning copper ions and electrons into solid copper. This transfer of electrons from the oxidation zinc, known as the anode, to the reducing copper, known as the cathode, creates a current that is used in batteries.
So to really showcase what we just covered in the previous section, Aiden here is going to show us how to create a battery right at home to just really secure these principles in our head. Using a copper coin as the cathodic electrode and using a nail as the anodic electrode, we are able to generate current by using the lemon juices as electrolytes and using a voltmeter to connect the electrodes together. The voltmeter reads a specific charge indicating the electropotential difference in the cell itself. How about a Tesla car battery? Within a Tesla car battery, they use lithium-ion cells, which, as the name suggests, is a redox reaction using lithium. Specifically, in a Tesla car battery, the type of lithium-ion cell they use is the lithium, cobalt, nickel, aluminum variant. In these cells, the anode electrolyte is graphite, the cathode electrolyte is made up of a combination of around 80% nickel, 15% cobalt, and 5% aluminum, and the electrolytes are lithium ions. Using our table of cell reduction potentials, and using lithium as a reduction half reaction, and the rest of the elements as oxidation half reactions, we get a range of voltage varying from 4.71 volts when aluminum is the cathode, 3.33 volts when the cathode is nickel, and 3.30 volts when the cathode is cobalt. Within the cell, it is typically structured as like the picture on the screen. To the left, there is a material, usually a metal used in a wire, that collects the electron connected to the graphite anode surrounded by the lithium electrolyte solution. In the middle, there is a semi-permeable membrane to separate the half cells. Finally, there are the cathodic electrodes on the right, also connected to a material which can collect and transfer the electrons. Rather than having huge secondary cells to create the necessary capacity for a car battery, Tesla does something completely different. They create a bunch of small lithium batteries, which they call the 21700. In order to match the capacity of other electric vehicles, these batteries are connected in parallel. What sets this technique apart from other brands' electric vehicles is that Tesla batteries can fit into any shape and any compartment, since you can make a circuit with small batteries in so many different ways. as it is incredibly small and can fit into any space. This allows the car design to be relatively independent to the needs of the battery, and thus making sleek and impressive looks feasible for the car itself. Unsurprisingly, the battery loses voltage when it is being used. We can actually calculate the change of voltage that the battery will experience by looking at the amount of products and reactants. Through what we learned in equilibrium, we know that a positive delta G means that the reaction is non-spontaneous, whereas a negative delta G is a spontaneous reaction. G being, of course, Gibbs free energy. We also learned in electrochemistry that a positive cell potential is spontaneous, so a positive voltage is spontaneous, and that a negative cell potential is non-spontaneous. Given that both of these values deal with spontaneity, we can actually find a relationship between the two of them. This equation on the screen shows a correlation between free energy of the reaction and the cell potential under standard conditions. It states that the change in Gibbs free energy is equal to the negative value of the moles of electrons involved with the reaction times Faraday constant, which is just 9.65 times 10 to the power of 4 coulombs per mole, times the cell potential. Not only does this equation showcases the relationship between Gibbs free energy at standard conditions and electric potential, but it can also be modified to work under any circumstance, i.e. non-standard conditions. Simply put, we can remove the naught from both delta G and E, and it describes the relationship under non-standard conditions as well. Although the Gibbs free energy value that we can calculate is useful, it doesn't really tell us how the voltage really changes when the reactants and products are not at initial values. However, if we recall, Gibbs free energy can describe the spontaneity of an equilibrium reaction at any moment. Furthermore, we know that in the real world, not everything is under standard conditions. Therefore, we need to find an equation that can find delta G at various situations. The perfect equation for our situation is the following. This equation on the screen showcases the correlation between Gibbs free energy at non-standard conditions while also relating it to the concentration of reactants and products in the reaction. It states that, quote, Gibbs free energy equals Gibbs free energy at standard conditions plus the ideal gas constant multiplied by the temperature in Kelvin multiplied by the natural log of the reaction quotient. Now, just a quick refresher, natural log or ln is just log base E, which is a number on your calculator for simplicity's sake. In case you don't remember what Q is as well, Q is the reaction quotient. It is simply just the concentration of products over the concentration of reactants at any given time in a reaction. Now that we have a way to relate Gibbs free energy to voltage, and a way to relate Gibbs free energy to the concentration of reaction, we can combine the two to find voltage at any given time. Substituting negative NFE at standard conditions for delta G naught, and just normal NFE for delta G, we are given the following equation. Negative NFE equals negative NFE naught plus RT ln of Q. Dividing all terms by NF, negative, we are given the following equation, which is commonly known as the Nernst equation. Voltage equals voltage naught minus RT over moles of electrons times Faraday constant times ln of Q. By substituting values of standard cell potential and the concentration of reactants and products for the reaction quotient, we are able to see the instantaneous voltage of a battery within a car. The importance of knowing the voltage at any given time comes from the fact that lower voltages are not able to power the electric motors on a vehicle as effectively. We've all seen electrical appliances, especially motors, run slower when the battery has less charge. Imagine if your car suddenly couldn't accelerate onto the highway. That is a serious safety concern.
Now that we know that voltage depletes as the reaction undergoes, we can understand why batteries lose capacity as time goes on. We've all witnessed our phones seemingly lose 10 to 20% charge in a blink of an eye. And why is that? Well, the main reason for the loss of charge is because of the diminishing amount of available lithium ions that can undergo redox reactions. Using Nernst's equation, we can see that the loss of lithium ions, which are the reactants, yields a greater value for Q. And this is because we are decreasing the denominator, thus increasing the overall value. We then take the natural log of Q and subtract it from E naught. This means that a bigger Q value will result in a greater loss of voltage. Therefore, we know that the maximum voltage in a battery will be less if there are less lithium-ion electrolytes available. Most commonly, the loss of available lithium ions comes from side reactions. These are reactions other than the expected redox reactions. Side reactions occur during the discharge and recharge of batteries. As the battery discharges, the cathode loses mass and the ions go into the solution. Within the solution, they will travel through the semi-permeable membrane and into the anodic half cell. Once in the anodic half cell, the metal ions will travel to the solid electrolyte interface region on the outside of the anodic electrode. This region is formed through the reduction of lithium ions and prevents the degradation of the graphite electrode. However, as the battery continues to react, the combination of the metal ions and the solid electrolyte interface region causes lithium ions to get trapped. These trapped lithium ions are unable to react further and cause the loss of free lithium in the cell. This limits the lifespan of lithium-ion batteries and puts a maximum shelf life for Tesla vehicles.
Although electric cars are praised for being environmentally friendly, the process of making lithium-ion battery is not. There are two ways to extract lithium, and the most common way is by pumping brine containing lithium salt to the surface where it is then let to dry. The resulting mixture of minerals is then treated to another pool called the evaporation pool, and various chemicals are mixed in and evaporated again to reveal the lithium powder. This whole process costs around 500,000 gallons of water in order to make 1 metric ton of lithium. This is not only harmful to neighboring ecosystems as you are using a lot of its water, but it is also a contributor to the water crises in countries such as South America where lithium is abundant. Furthermore, the chemicals needed in the evaporation pool are incredibly harmful if not treated properly, as they contain such chemicals like hydrochloric acid. Unsurprisingly, if these chemicals were to get into the local water system, the entire ecosystem may die. And this is actually what happened to Ben. The evaporation pool solution poured into the environment, and fish were found dead in the streams, and all other animals that used the water for hydration were found dead as well. It isn't just the extraction of lithium that isn't environmentally friendly, as the creation of the battery itself produces an incredible amount of carbon dioxide. A poor gas mileage car vehicle that uses fossil fuel can travel a distance of over 11,000 kilometers, and that amount of carbon emissions would only equal to the amount of carbon emissions needed in order to create a lithium-ion battery. Knowing this, if you are switching to an electric car vehicle from a gas-powered one that is still healthy, it is actually more detrimental to the environment. You should use a gas-powered vehicle until the end of its lifespan. Then, when you're given the opportunity, switch over to a zero-emission vehicle that uses a lithium-ion battery and use it to its fullest potential in order to save on carbon emissions.
Overall, we were able to showcase how a battery really works and the principles behind a lithium-ion battery within a Tesla vehicle. We covered concepts linking electrochemistry to equilibrium through Gibbs free energy in order to expand and connect what we have learned in class this quadmester. Using this knowledge, we were able to understand how side reactions are able to impact a car battery's lifespan and decrease voltage. Lastly, we hope that we were able to educate everyone on the potential environmental impacts that the production of lithium-ion batteries could have on the environment. We hope that you've learned a lot from this video, and we hope that you have gained a lot of knowledge. Thank you for watching. Let's go.